When looking at these integrals with quadratic denominators, we look for various things. This first one is straightforward because the derivative of the denominator is just sitting there in the numerator. So if the numerator is the derivative of the denominator, great. It's going to be a logarithm, isn't it? So that's very straightforward. It's like when you're factorising, you always take out a common factor. We'd be looking to see if you've got a quadratic denominator, and that's what we're discussing over the next few lessons, is the numerator the derivative of the denominator? Well, yes. So the answer to this one is that it's the natural log of the denominator plus c. So that's a straightforward one. Let's call that type 1. Right? Let's call that type 1. And it's going to keep cropping up as a part of some of the other types of integrals with quadratic denominators. So they may have their overall technique, but in the midst of that, you'll end up probably with one where the numerator is the derivative of the denominator. What about this one here? It's a quadratic, which happens to be a perfect square. I could have been annoying. I could have written it out as please find the integral of 1 on x squared plus 6x plus 9. And look, they would be expecting you to notice that in the HSC, that is just the perfect square, 1 on x plus 3 all squared. Well, what about that one? Well, that one also is fairly straightforward, like from the Mathematics Advanced course, just like type 1, where the numerator is the derivative of the denominator. This one here is a fairly straightforward one because in the advanced course, we've actually learnt how to do the integral of something like that, where you just have a quite simple linear function being raised to a power. So it doesn't require a substitution or anything. That one's quite straightforward. You would just increase the power by 1 if you're integrating. I'd throw a minus out here because minus 1 times minus 1 times 1 times x plus 3 to the minus 2 if I was to differentiate, plus c. So it ends up being negative 1 on x plus 3 plus c. It's fairly straightforward. But we're going through some types of things where you get a quadratic on the denominator and you're asked to integrate. So check if it's the logarithm type. Check if it's this type 2, straightforward type 2, where the denominator is a perfect square. So there are a couple of ones where you get out of it easily. What about this one? It's not a perfect square. Looks close, but it's not a perfect square. The denominator, well, the numerator is not the derivative of the denominator, so we've got something else happening here. What do we have? Well, we don't have a middle term in a quadratic, like in terms of ax squared plus bx plus c, the standard type of quadratic that you might encounter. In this case, there's no b term. It's just x squared plus 9. So that's one way you could think about it. There's no b term. The other way you could think about it is just you can't factorise that denominator. If I'd had a minus 9 there, you'd be able to factorise it and I'd be putting this under a different category. So either in this case, notice that there's no b term, or in this case, notice you can't factorise the denominator. So what are you going to do? Well, there's some standard integrals that you're supposed to know, and this one would come from the Extension 1 course. And the standard integral that we're talking about would be the inverse tan. So the rule that you would see for inverse tan on your formula sheet is that the integral of f dash x on a squared plus f of x squared dx is equal to 1 on a inverse tan f of x on a plus c. So that's the rule you get on your formula sheet, which you can apply to this one. I guess it's twisted around a little bit if you wanted to actually see that relate very easily to what's going on. You could change this integral here to be in this format. So 3 squared and x squared. Okay, and the function that's being squared here, the actual function that's being squared is x. And the derivative of that function, the derivative of x, is 1. So this is fairly straightforward, really. If you look at the purple formula that's on the formula sheet, you'd notice it's directly an inverse tan question. And the answer would be, of course, that would be 1 on a, so 1 on 3, inverse tan of x, because the function is just x, on 3, plus c. So that's a fairly straightforward one. And I would like to say maybe that's type 3. Now, it's not as easy as the first two, where we just talked about the logarithm type, where the numerator is the derivative of the denominator. We talked about the type where we had a perfect square on the denominator and just some sort of constant on the numerator. And that was a straightforward one from the advanced course. Now we've moved into straightforward ones, but they're from the Extension 1 course, where you have to know how to find the integral of inverse tan and just recognise that. So remember, we're talking about quadratic denominators and the different types and how you might approach them. Well, what's going on with this one? Well, the numerator is not the derivative of the denominator. The denominator is not a perfect square. So we're left with the type that you can't factorise the denominator. And when I get ones that I can't factorise, I start to think it could end up being an inverse tan, but I'm going to have to put it in that format. So the trick here would be to complete the square. That's what we'll need to do with this one. So we will end up with the integral of 1 over x squared plus 4x. And in here, what did we have to do? We had to add on half of the coefficient of x squared, and we better take that off as well. So this is actually the integral of 1 over x plus 2 all squared, 6 plus 2 dx. Now you're going to need to get that in the format where you can do the whole inverse tan on it. So you need to make sure you write it in the format that's available on the formula sheet. For example, the formula sheet says we want the integral of f dashed x on a squared plus f dashed of x, not f dashed of x, just f of x squared. If it's in that format, that will be 1 on a inverse tan of f of x on a plus c. I'm struggling to fit in the plus c these days. But that's what it'll be. So I have to pop it into that format. And at the moment, my question is x plus 2 all squared plus 2 dx. So it's not quite in that format. Let's reverse these around. 1 on 2 plus x plus 2 squared dx. All right, so at least I've got a squared plus f of x squared. What would a squared be? It'd be root 2 squared. 1 on root 2 squared plus x plus 2 squared dx. All right, the function that's being squared is x plus 2. What's the derivative of x plus 2? 1. Oh, good. So we have the situation where we've got the derivative of the function over a squared plus f of x squared. We can just write down the answer directly from that. This is equal to 1 on root 2 inverse tan of f of x, which is x plus 2, on a, which is root 2, plus c. So these ones are ones you need to look out for, which are to do with inverse tan. And just let me recap where that came from. It was a quadratic denominator that couldn't be factorised. It wasn't a perfect square. The numerator was not the derivative of the denominator. It couldn't be factorised. So I completed the square and happy days, I ended up with an inverse tan. Now clearly there's just a constant on the top here too. All right. This one here is looking very much like the ones that we started with. This one here looks very much like the numerator is the derivative of the denominator, except the denominator's derivative is 2x plus 5, and this is 2x minus 3. So I'm going to say that for this one here, this will be like my type 5. And it's where the numerator is almost the derivative of the denominator. Almost the derivative of the denominator. It's pretty close. So we will make it be the derivative of the denominator and see what comes of that. So this will be the integral of 2x plus 5, because the derivative of x squared minus 5x is 2x plus 5. But it's supposed to be minus 3. So instead of plus 5, I've got a minus off 8. Now I'm able to split this up into two different types. So if I just put this up the top here where you can still see it. This integral is the same as 2x plus 5 on x squared plus 5x plus 7 minus 8 on x squared plus 5x plus 7. So now we've got two different types happening, don't we? And we're going to have to do a bit of work here. But this one is going to eventuate in a log. This one is going to be one of the ones we talked about where it's not a perfect square and I can't factorise it. So when it's not a perfect square and I can't factorise it, I'm going to end up with one of those guys. I'm going to spend some more time on this particular one later and work it out, but I want to run through you the different types that we're going to come across. We'll come back and we'll focus on some of these ones that we've got up to so far. We're up to type 5. Type 6. This is like a improper function, I guess you might call it, an improper function. What do we mean by improper function? Well, clearly the top has a higher power than the bottom. And look, this is going to work with any improper functions, but we're talking today about quadratic denominators. So x cubed over x squared plus 1. What are you going to do with this type? Well, this one here, we could use polynomial division to turn it into some types that we've already come across. So, I'm calling this type 6. But it's actually where you can see you've got to split the polynomial up using polynomial division, split the function up, and then apply some of the previous types that we've already done. What we also often need to apply to this is partial fractions, which is a type that's coming up. But it's the key to doing this one is to be able to rewrite it. So I'm going to actually do this division. I'm trying to divide x cubed by x squared plus 1. That's what it says up here. X cubed divided by x squared plus 1. So I might actually do the polynomial division. X times x squared is x cubed. X times 1 is x. So subtract and I get minus x. What I've just found is that x cubed divided by x squared plus 1 is equal to x cubed divided by x squared plus 1 is equal to x, and this bit left over. So I did my polynomial division. Okay, now, if I can just grab paper here to work with. Done my polynomial division, and my integral of x cubed on x squared plus 1 dx becomes the integral of x minus x on x squared plus 1 dx, which is now the integral of x, which is half x squared. We can do that easily. And the integral of x on x squared plus 1 dx. Now, this last one, we can see, I'm not going to go through this now, I just want to run through some different types with you, but that's straightforward, that's advanced maths, right, half x squared. This one here is straightforward. It's going to be a log, but you're going to have to put a 2 there and a half there, aren't you? So that the derivative of the denominator, which is 2x, and we'll be able to work that one through. So we'll do that later on. We'll work that one through. But for the time being, I just wanted to have a look at what some of the different types you're going to come across for where there's a quadratic denominator. We're nearly there, so hang in there. The next different type that I'm interested in is one that is of the format that we've got here. I was talking before about denominators that you can't factorise. Well, can you factorise this one? Because if you can, then we've got our last type. I think I'm up to type 7, right? Type 7, you can factorise the denominator. You can factorise the denominator. So if you can factorise the denominator, we're going to write it as partial fractions, which is a whole nother lesson. But let's just see if we can write this out factorised. Well, two numbers that times to be minus 3 and add to be positive 2. So it's x plus 3 and x minus 1. So I could factorise the denominator. Now, we're going to show in the next lesson that this can be written in the form, in a different form by using partial fractions. So I'll just, instead of going through the whole process now, I'm just going to point to partial fractions. If you end up with partial fractions, you're going to end up with things that are logs. You're going to end up with things that are inverse tans, or even simpler integrals when you split them up into partial fractions. And I just want to leave that thought in your head as we just look at what can happen in terms of the partial fractions. So we haven't done this one yet, but we will. We'll get there. But I just want to point out that there's various types that you can use partial fractions for. Something like this one here. Because it's factorised denominator, this one you can see that they're linear factors because the thing inside the brackets is like a equation of a line as such, ax plus c. It's a linear factors. This has actually got a repeated linear factor, so there's going to be a special method for that. This one here is going to be partial fractions because you've got a denominator that's factorised, and it has a quadratic factor, so there's going to be a special thing we do when we work out partial fractions for quadratic denominators. And this one here has got a repeated, it's got a couple of quadratic denominators in there. So there's going to be some special techniques we use for that. And if you repeat the quadratic as well. But that's another lesson, just to point out that if you can factorise the denominator, and in particular, if you can factorise it when you're working with a quadratic denominator, which is what we're talking about today, then you're going to use this technique of partial fractions, which will be our next lesson.